And then our final speaker today is Sam Speight of the University of Birmingham, who will be telling us about powerful combinatory algebras for intensional time theory.
Cool, thanks. Thanks to the organizers for organizing. It's the opportunity to speak. So, yeah, I guess, yeah, so I'm interested in, set this work in context, I'm interested in building realizability models of intensional type theory, intensional Martin-Lipp type theory, maybe one day homotopy type theory. So what we're going to do here is kind of think about what realizers could be in this context. Yeah, so by way of motivation, I want to take us back to BHK interpretation. It's often said that realizability formalizes the BHK interpretation. So the BHK interpretation, it specifies what counts as evidence for a given proposition, right? So evidence for a conjunction is a pair consisting of evidence for the first conjunct and evidence for the second conjunct, etc., etc. More recently, we have the homotopy interpretation of type theory, which maintains that to put it in a kind of BHK style, evidence for an identification is a path in some space. So this leads to the idea of having realizers themselves carry higher structure. So in a realizability interpretation, formal realizers play the role that evidence does in the informal BHK interpretation. So we would like kind of realizers that are paths between realizers at a lower dimension that can play the role of evidence for identifications. That's the kind of philosophy. Yeah, and so I should mention that these guys do kind of have this kind of philosophy when they develop cubical computational type theory. So the realizers are expressions in kind of cubical programming language, so in have higher structure in that sense. But I guess I'm interested in kind of the categorical approach to realizability, and in the traditional setting for this, realizability models are most often built out of PCAs, partial combinatory algebras. So let me just say briefly what those are. So a PCA has a carrier set, and it has a partial binary operation application. And then we require that there's these combinators, which, I mean, there are kind of various ways to do this. Here, I've chosen K and S. So these special elements that satisfy these equations here. And I guess the upshot is that that we get a property known as combinatory completeness, right? So we can simulate lambda abstraction, and together with application, this satisfies a kind of beta law. Right. Some examples. So I'm going to talk through 3 examples, probably the first kind of 3 examples you would come across if you were to read about PCAs. And later I'll give kind of higher analogs of these three examples. So the first one is lambda calculus. So we take our PCA, the underlying set of our PCA, to be lambda terms. We can take closed lambda terms modulo beta. Then application really is just application in the calculus. And the combinators are defined like that, which you might expect by looking at the required equations. Cool, that's example one. So example two, categorical models of the lambda calculus, by which I mean Cartesian closed categories with a reflexive object. So should you draw a picture? So a reflexive object for U is an object such that it's the function space U to U is a retract of U. So
It's not great.
oh, should I try green?
Yeah.
Better? Cool. What have I called these? So cool. So we have a section which is often called lam and a retraction app. So the composition of these is the identity. Right. That's the beta law. If you had app followed by lam is the identity, then that would be easy. So given one of these structures, so a Cartesian closed category with a reflexive object, then we can build a PCA. The carrier is a set of global elements of our reflexive object, and application is induced by this morphism. So we post in the, if you use the lambda calculus as an internal language, then it really is just application of the lambda calculus again. Cool. Right, so that's the second example, and both of these examples are actually total PCAs, right? We can always, the lambda calculus, we can always apply one term to another thing. Okay, final example, which I guess is kind of the prototypical example, known as Kleini's first algebra. So the carrier set is the natural numbers, and application is defined as follows. So n applied to m returns the value, if it exists, of the nth partial computable function applied to the number n. And we would use the universal function theorem and the SMN theorem to prove that this is a PCA, and it's a genuinely partial combinatorial algebra this time. Okay. So far so good. Okay, so to kind of frame what we're going to do next in kind of general context. It's nice to mention that that PCAs can actually be defined internal to any Cartesian restriction category. This is due to Cockett and Hofstra. So restriction categories, well, I guess they've kind of come up a bit already this week, just implicitly. Axiomatize, categories of partial maps, and Cartesian restriction categories have a suitable notion of product. I won't give the full definition. Actually, we're just going to be working with a couple of Cartesian restriction categories. But I guess the prototypical example is sets and partial functions, and then of course every category of finite products is trivially Cartesian restriction category. So the Cartesian restriction categories that we're going to be interested in are the trivial Cartesian restriction category of groupoids and functors between groupoids, and also the non-trivial Cartesian restriction category of groupoids and partial functors, by which I mean functors defined on well, for the examples that I'll give, we can say some full subcategory of the source. Right, so the definition in this setting, so PCA in a Cartesian restriction category now consists of an object in the category and a map from so an object A and a map from A times A to A. Then we can define these two maps here that correspond to the K and S combinators that we've already seen. And then we require that these two maps are computable in the sense that there's a total map. So there's a code. So a map F is computable if there's a code living in the carrier that yeah, I guess computes the application like the original map F. Right, so in the case of groupoids, right, we have like a PCA in groupoids, we'd have a carrier groupoid, and the application would be a functor or a partial functor. Yeah, so that's what we're going towards. We're going to give examples of PCAs in Cartesian restriction categories of groupoids. Yeah, realizing this idea of having realizers with biostructures. Okay, so first example, which is meant to correspond to the first example earlier, the lambda calculus. So this is a cubical untyped lambda calculus. So inspired by cubical type theory, which is yeah, so a computational interpretation of homotopy type theory. So it's inspired by cubical type theory in the sense that that we have not only a context of kind of regular variables, but the context of dimension variables. So we think of terms in a empty dimension context as just points, and then we think of terms in a singleton dimension context as so paths between points, and you can go higher and higher, but we're happy for the moment with one foil stuff. And insofar as we're happy with one groupoidal stuff, the kind of cubical approach is well, I mean, we can do I guess globular lambda calculus. So what we do, as well as the kind of usual rules for lambda abstraction application, we have constructors for composition, for instance. So this rule here is telling us that given a path alpha, so alpha lives in a singleton dimension context, so it's a path. Same for beta, and if we can show that their endpoints match up, so I guess I should say, so we have constants 0 and 1, which thinking of as endpoints of an interval. So if we look at the start point of the path beta, and that matches up with the endpoint of the path alpha, then we can compose these two. Then units. So identities are just given by weakening in the dimension context, right? So if alpha is some path, then this is saying that I guess alpha composed with the identity of the at the codomain of alpha is just alpha. So yeah, that's just I guess a sampling of the rules, but once you write everything down, the idea is that you get you can form a groupoid whose objects are terms which are closed with respect to the dimension context, so points, and whose morphisms are terms in a so it's a morphism from T to U is some path alpha that whose start point is T and whose endpoint is U. So we get a groupoid in this way. And then the application functor, again, is just given by application of the calculus. And the combinators are as before, this one, closed with respect to regular context, dimension context. So this gets us a total PCA in the trivial Cartesian restriction category of groupoids. Okay, so that was example. That was example 1. Example 2 at the groupoid level. Example 2 at the groupoid level. Corresponding to categorical models of the lambda calculus, bicategorical models of the lambda calculus. So a bicategorical model of the lambda calculus is a Cartesian closed bicategory with a pseudo-reflexive object. So whereas in the one categorical case, we had that this composition or this diagram commute strictly. In the bicategorical case, we would just say we would allow this to commute up to some invertible use. And there are in fact a few examples of these that already appear in the literature and been studied for people have studied them for their own reasons. So generalized species of structures. And then I guess, categorifications of some models of the some kind of known models of the lambda calculus. So profunctorial Scott symmetrics, categorified relational model, distributors induced model, categorified graph model. These are the ones that I've managed to find anyway. So given bicategorical model of the lambda calculus, we build a PCA by whose carrier groupoid is the core of the Hom category 1U, and then application is induced by the same map as we had before. So yeah, something interesting happens here. So these PCAs are total, but now they are weak in the sense that the combinator equations fold up to isomorphism, right? Just which comes just from the pseudo-reflexive object. Cool. Okay, so that's example 2. And then, finally to I guess the most the kind of speculative example at this point. This is kind of a first pass at defining, formulating a categorified clean dispersed algebra. So instead of working over the natural numbers, we're going to be working over the finite sets and bijections between them. So beefed up natural numbers. I guess this is a natural numbers object in group points in a 2 categorical sense. So we're going to fix an equivalence from this category to its skeleton of finite ordinals and permutations, automorphisms. And we're going to define a notion of partial recursive functor with respect to this equivalence. So what is a partial recursive functor? It's a functor of this shape belonging to the smallest class containing, well, the constantly 0 functor, the projection functors. I mean, there's design choices here, right? So the way I'm doing it at the moment, constantly 0 functor, projection. We can take the disjoint union with any finite set C. And then we want to close under composition. I think all of those are kind of no fuss. And then we also want to close under primitive recursion and minimization. So let's look at primitive recursion. So if you kind of squint, then these are just the kind of usual equations for primitive recursion. But now x's and y's are ranging over finite sets. So we have a base case, and then we have a recursive case, and this is where I guess this equivalence comes into play. So it's allowing us to count basically. So we can count down and do our recursion. And then kind of similarly for minimization, if you squint, this is just the usual thing, but this functor is just allowing us to count. So very much work in progress, but the idea that I have is that this should be a genuinely partial PCA and weak in the same sense as before, right, with the bicategorical models of the Land Campus. Yeah, so the universal function and Esselman theorems might hold just that isomorphism. Work in progress. Cool. Okay. So yeah, there's 3 examples. So kind of going forward, I guess it would be nice to have a definition of a weak PCA in a Cartesian restriction bicategory, something like that, right? So you notice I kind of stopped short of giving such a definition. I guess for at least 2 reasons. I don't know if anybody has written this, what this notion is, written down what this notion is. Maybe that's not so difficult. But also, when it comes to coherence of the cells witnessing the combinatorial equations, yeah, I'm not so sure what, if any, coherence conditions we should require. A good kind of check for any putative definition would be, I think, to because these things are well studied well enough by categorical models of the lambda calculus. What you could do is take your definition of a weak PCA, do a kind of bicategorical Karoubi envelope construction, idempotent completion, and if you got out a bicategorical model of the lambda calculus with all its coherence and whatnot, then that for me would be a convincing kind of check. And then, of course, we want to actually do realizability of these things, right? So this talk, I guess, was to try and convince you that like this is a reasonable idea, that there are examples of stuff we can do. It's kind of realizability over. So the idea would be, I mean, I've explored doing like categories of groupoidal analogs of partitioned assemblies, for example, not over these. I mean, over kind of different gadgets that of realizers that carry high structure. And I'm kind of looking into what per models, like proof relevant or high categorical per models would be. Assemblies, arbitrary kind of general assemblies and realizability forces. Somewhere down the line, that would be really nice. So yeah, what do these putative models look like? Yeah, I think that's all I want to say. So thanks for listening.
Thanks for your talk. Do we have any questions for Sam?
Yeah, thanks. Firstly, thanks for the talk. I was wondering with your notion of a two-dimensional natural numbers object. So, well, I mean, there are many different ways of saying what a natural numbers object is in the one-dimensional setting, but the usual way that you say it is that you have, a zero and then a successor, and then it's the kind of free thing that looks like that, free algorithm or something.
Yeah.
Is that is there an analogous definition that you're using that the kind of universal property holds up to isomorphism?
Yeah, that's what I had in mind. Yeah.
Right. Okay.
But I am, yeah. Yeah, no, I think that is what I had in mind.
Thanks.
Yeah.
Any other questions?
One way realizability is used is to show dependence of various principles, give models in which various principles, like in intuitionistic analysis and so on, are either verified or refuted. I mean, are there natural properties? I mean, in the hierarchy of intentionality, like extensionality properties in type theories. We obviously haven't got to univalence yet, but
yeah,
sort of function extensionality and so on.
Yeah.
So they're natural candidates for things you would try to either
realize,
verify or refute.
Yeah. So I guess it'd be nice to have a model in which univalence holds and Church's thesis holds, something like that. So there is a model in, so a kind of an alternative approach to kind of realizability for intentional type theory is to take a like a classic, classical model of realizability model of extensional type theory, just assemblies over Kleini's first algebra, and then look at higher structures in that. So cubical assemblies, which are cubical objects in assemblies over K1 have been studied. So in that model, Church's thesis doesn't hold, which you might like it to for a realizability model. It holds in some kind of sub model, but kind of a kind of think it's still open to get a kind of higher realizability model that satisfies univalence and Church's thesis in the full model, I guess. Yeah. So yeah, that would be one thing.
Anybody else? Yes, I have a question. So you mentioned notion of partial functor. Is this sort of spans with a monarch or more or less left-legged cat?
Would it turn out to be the same thing? It's already,
But then my question is, what happens to the two cells?
yeah. Yeah, I kind of glossed over that, I guess. But yeah, I guess yeah, partial natural transformation. I mean, if you take well, partial functions to be defined on full subcategories, then I think it's kind of nice enough.
It might just be that one. Yeah.
Natural transformations on the main,
Yeah.
yeah, that's kind of what I had in mind. Yeah.
So if there are no other questions, I'll thank Sam.